Hello, my name is Jim Clodfelter. I'm the Marketing Manager with the Light Brigade, and we welcome you to today's webcast brought to you by Lightwave and sponsored by the Light Brigade. Today's event, Fiber Optic Connectors, the bottom line is still performance, will be presented by Larry Johnson, the Director and Founder of the Light Brigade. This presentation is both live and interactive, so you can ask questions at any time by typing your question in the Ask a Question area down in the left-hand corner of your screen. If you're running pop-up blocking software, you'll need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. A couple other housekeeping things. For your convenience, this presentation will be available on demand 24 hours after this live event, and you will receive a reminder email message which will be sent to all registrants. It'll give you access both to the location and via the homepage on Lightwave Online. In addition to supporting audiences on the internet using Adobe Flash and Microsoft Windows Media, Penwell now offers webcast viewing via tablets and smartphones. You will now have a seamless access to both live and on-demand web presentations. One other opportunity too, if you do have technical questions, you can also type those into the question box, and we'll get back to you as quick as we can on those. Now it gives me great pleasure to introduce Larry Johnson.
Hello everyone. Appreciate you taking time from your busy work day to participate in this session. Little background on the Light Brigades on screen now. We always prided ourselves in our strengths of our instructors, technicians, the content that we teach, the equipment that we used based on technology, but also very heavy on standards. And I'm going to relate to those throughout the session today as well. It's been fun since the founding in 1986 because along that time, the fiber optics industry has evolved tremendously. When I first started in fiber in 1977, the very first installation in North America had just taken place. So I was literally involved with the fiber, the cable, the connectors, test equipment testing, and then of course as technology evolved, we saw massive improvements, which today are taking us closer and closer to the user, whether at the home or the business. And so let's go to the next slide. This was a shot that I put together maybe 10 years ago, but it was just showing the proliferation of different types of fiber optic connectors that were available at that time. And even if you notice at the top versus the bottom, the cordage colors is basically we were talking about multimode, what would today be called legacy OM1, 62.5, 125 micron fibers. And down at the bottom is a single mode with the yellow color codes. And these color codes are standardized by the TIA 598 color code standard. And but anyway, what you're seeing is a lot of different connectors that have evolved. And for those that have been in the industry for a while, you probably see quite a few of them up there that are no longer around or available. But legacy systems still may use these connectors. So as we progress, I'll talk a little bit more about some of the features that are key to connectorization, connector performance, and fiber tolerances in general. So in this case, what is a fiber optic connector? Well, let's talk about more what does it do versus what it is. So its function is to minimize the optical attenuation across an interface. And most fiber optic connectors are in-line types as shown. This happens to be an SC connector, a single mode with a UPC polish. Now I can tell that because single mode because of the yellow cordage, number one, the blue color code on the plugs and the adapter, number two, and that also tells me the spherical polish versus an angled, which would have been a green color code. But the second function of the connector is to minimize the reflectance. And we're going to talk about reflectance versus ORL, or optical return loss, as well. There's a couple other features that you'll notice on these on the photographs here. The body of the plug has a key on the left and right side. The blue obstruction, we'll show a diagram later, and then the adapter in the middle has a keyway. That performs a good alignment from the external side, but the critical alignment's internally, and we'll discuss that in a few slides forward as well. But We also need to provide the mechanical and environmental protection. So in other words, this connector has to work over a period of mating cycles, and most connectors are designed for 500 mating cycles with a repeatability specification of 0.2 dB. Okay, so if we look at where we continue from the connectors, is where are they used in the network? So first on the diagram, from left to right, we see an EO device, and on the right side, an OE. EO means electrical to optical. So in other words, a laser or a light-emitting diode in a transmitter. And at that interface, we have a connection on the transmitter side. We have a cross-connect panel. We have a jumper or patch cord used to link the two. And then we have our fiber span, single mode or multimode. And then at the far end, again, we reverse the process through a patch panel, and then again we have the connector on the receiver. Now that could be different types of connectors, and we'll explain different points of this. But if it's a multi-mode connector, most likely it's going to be field terminated, and in the single mode world, it's most likely going to be factory built for various reasons, which we'll discuss. There's different locations where cross-connects are located in a network, and in the case of a premises application, there are going to be more connectors in a closer span, where on a long-haul fiber link, they could be 20, 30, 40 miles apart very easily with one connection at each end. Again, we have to deal with the attenuation of the span, but we also have to deal with the component attenuation, which we're going to review the standards. We also have to deal with the reflectance values of those connections. And for those that are involved with terminating and installing fiber optic spans, the organization of the connectors and the panels. In this case, we show different connector types. Up at the top left, we see another example of the inline connector. We also show at the lower left an active device receptacle. And the term here is receptacle. The receptacle is considered when an LED, laser, or a photodiode is housed in a connector itself. So on a piece of test equipment, for example, a handheld power meter, you probably have on the outside your connector interface, but internally you have the device directly installed in that. On the other case, if it was a PC board, you would have a pigtailed plug assembly with an inline adapter on the front interface, with the pigtail going to a laser diode or a photodiode, and it being spliced or bonded into position. Now the military I put in here, and there's all sorts of tactical connectors and variations used for various industries. But instead of the terms as ferrules, they'll typically use the term termini instead. And normally you have a male termini on one side and a receptacle termini or female termini on the opposite side. A little more difficult to terminate as well. Also extremely rugged and can be very expensive, and so you don't want to make mistakes. You want to get the best yield possible. And we're going to spend, at the end of this presentation, 6 slides just on the topic of yield. Other variations of connectors are the attenuators and the terminators. Attenuators are those that add loss intentionally to a span, and this is to decrease the optical power level coming into a photodiode, because photodiodes can be oversaturated with light. And in other words, we have to diminish the value of that light coming in. In other words, like putting sunglasses on in warm and sunny days when you go outside. We bring down the light level so we're within the acceptance region of a photodiode. Terminators is a device that literally terminates the optical signal, and in this case it can dead end a reflection, so they are used to prevent Fresnel reflections at open connector ports, splitter ports. They can also be used with OTDRs to test far end Fresnel reflection values as well. Okay, on the following slide we now show a diagram showing what a connector breakdown appears like. And this has the SC connector as the diagram. And from the rear of the connector, we see the strain relief boot. And then from the front of the plug, we see the ferrule, in this case a 2.5 millimeter ferrule. And then at the top of the diagram, you see the key. And the key aligns with the key slot or key way in the adapter. Internally, because most cordage is meant to prevent damage and for handling patch cords and jumpers. Normally a 3 millimeter cordage is standard for the larger SC, ST, FC type connectors. So we have an aramid yarn, also known as Kevlar, a DuPont trade name, that's used for the strain relief mechanism. And we have the coupling mechanism, and each of these different connectors has different types. Most common today is the push-pull coupling mechanism. And then inside the ferrule itself in the body, we decrease the diameter from a 900 micron coating to, we strip this back and insert the 125 micron fiber. Now, one of the key points that we need to discuss and be aware of is that the fiber tolerances are very practical and very real, and that in multi-mode fibers and single-mode fibers, there's different numbers for the core diameter, the cladding diameter, and at the same time ovality, or how round the fiber is, the core cladding concentricity, how centered the core is in the fiber. You also have the tolerances of the ferrule itself, which is the inside diameter of the ferrule, and you have in the adapter, the sleeve itself, the internal alignment sleeve, also has plus or minus tolerances. So when you start talking about the performance of a connector, you can never forget that the connector is only as good as the fiber tolerances, and anybody that's fabricating assemblies is always having to deal with these tolerances. And for those that are in the field that are going to be doing field terminations, they also have to address tolerances, and this is why sometimes you may find that a plug may be very easy to dry fit on, in other words, put the connector on without any epoxy in it, and then another one can be very tight. Well, that's normally your fiber tolerances from an OD perspective. A couple bullets here is the precision components are the ferrule and the internal alignment sleeve, also sometimes known as a C-clip, but they don't have to be a C mechanism. They could be just a precision clip. And also, where does the damage or contamination occur? So if we look at contamination, it can occur at the face of the ferrule and on the side of the ferrule, and in the alignment sleeve, the adapter itself, can happen inside. Now, the reason is that I'm saying both on the surface but also on the outside is if you don't just clean the surface of the ferrule, any contamination on the outside of the ferrule can be pushed forward or back into the connector. And this can also cause future damage if it's not cleaned properly as well. So what to look for in a connector? We've mentioned attenuation, repeatability, reflectivity. So here we see a couple values. On the top, excuse me, 0.5 dB per the ITU's T. I'll just forget the ITU-T. I'll just normally say G.671 standard. But this is the standard, the international standard for passive optical components. And connectors are passive optical components. And this standard specifies a 0.5 dB per connection. That's not per plug. That's a mated connection. And sometimes people say, well, it's 0.5 dB per plug. No, it's the full mated connection. Meanwhile, in North America, the TIA 568 standard specifies a 0.75 dB per mated connection, and because that standard is predominantly multi-mode, even though it does specify single mode, the value is much higher. Single mode specifications tend to be lower, and the G.671 focuses on single mode. Also, the Telcordia General Recommendation 326 specifies a 0.4 dB mated attenuation value. Some other values that are helpful. Telcordia, the same document, is a 0.2 dB repeatability specification. This is an excellent value for those that are troubleshooting connectors, because if you get a base measurement and you remove the connector, plug it back in, if it is higher than 0.2 dB on the repeatability, you probably have either damage, contamination, or wear problems, and it's pointing to that connector. So if you're testing a spanner, you're having problems, isolate which end you're doing the repeatability so you know which connector is good or bad before you start cutting connectors off. Two other bullets, the reflectivity. If you notice, we did not give you values here, and the reason is the reflectivity values change with different types of transmitters, especially laser diodes and specifically distributed feedback lasers and Fabry-Perot lasers. So the manufacturer of the system knows the type of laser, and they can say that to meet this qualification or quality of signal as a bit error rate, for example, you have to have a reflectivity of 55 dB or 65, et cetera. And so that value is normally a system-related value versus just a standard value. However, in the multi-mode world, there are values put out by the IEEE 802.3 of 20 and 26 dB for multi-mode and single mode. But that's because of the LED and the VCSEL light sources being used. They don't use the FBs and FPs at 850 nanometers. And again, the connector has to be rugged. So what is attenuation? Several things. One, you have to understand what it is and where it applies. So we deal with components and we also deal with systems. But what we want to do is maintain a quality level by manufacturing products that achieve low attenuation values, low reflectance values. But attenuation and optical system links can be identified in three categories. Those are the intrinsic, in other words, those that you cannot control. That's because they're based on the fiber itself. You can't take attenuation out of a fiber, and that whether it's absorption or scattering. Extrinsic losses, though, you can control, and these are the ones that a designer specifies, for example, says how many connections in a span, what's the loss per those connections. So these can deal with the fiber tolerances, they can deal with the bonding technique, the polishing technique, the quality of the lapping film used for the polish, the cleanliness, etc. Intrinsic, extrinsic is where we tend to get into problems, and a good example of this is when you have a single mode G.652 fiber in your cable span, and now you change to a pigtail to splice onto it, and it's maybe a G.657. Because pigtails tend to be short, you're within the dead zone of an OTDR, so you can't see the value or where the cause actually is. But where you get is sometimes a mismatch of either fiber types, fiber manufacturing processes, or fiber tolerances. So you need to know what you can and cannot control. And then again, we're going to talk more about test and document accordingly using the correct equipment. In other words, if you're doing multi-mode work, then you're going to be using different types of equipment, different wavelengths than you would in single mode. So you need to really have the right type of equipment to measure and document the tasks that you're performing. So what causes attenuation? These are cleave quality, and for those that are using the newer generation of splice-on connectors, the quality of the cleaving tool is critical for having good low attenuation connections. And that in separation does two things. One, as you can see, as the fiber, the energy emits out of the core, defined by the numerical aperture of the fiber, is the beam spreads. And the further the in separation, the more attenuation you're going to have. That's one technique for making a variable attenuator is to increase the gap between the plugs, or the mating surfaces. Another issue with the end separation is the amount of reflectance. It's a highly reflective. Anytime you have an air gap, you're going to have a reflective event, and it's very high, and normally we do not like to see any kind of end gaps or end phase separations in connections. The other is lateral offsets of cores. This is dealing more with fiber tolerances, but again, it could be a ferrule or a sleeve tolerance that can make this occur. Core mismatches can be a tolerance of the fiber, for example, 125 microns plus or minus 1 micron. Well, that means that you could have a 124 to a 126, and depending on the direction of the test, is your attenuation is going to be better or worse. Angular misalignment, this could be a polishing issue. It could be just a tolerance itself, and that on the connections. And very minimized, a cleave, for example, could be angular, and then splice, and so we have higher attenuation. And here's a chart that shows some of the polish values. And today, on the multimode polishes, almost all are flat contacting polishes. And even though the ferrule end face can be slightly spherical, the fibers themselves are mostly flat polish, and this is with people doing the standard figure 8 polishing. And it's a highly reflective surface, and this would be unacceptable if it was using a DFB or a Fabre-Perot laser to get a 20 dB reflectance. On the single mode polishes, these have evolved over time. The premise value is actually the IEEE 802.3 standard for Ethernet on single mode fiber. Totally unacceptable in a service provider world where even 20 years ago the physical contact or PC polish was 40 dB. Later it improved to the super physical contact, the 45. Today the highest degree of spherical polishes is the ultra physical contact at around 55 dB. And then for systems that are analog-based, dense wavelength division, multiplexing based, very high speed, the angled physical contact polish is the best. This has the lowest amount of light being reflected, and this is where these tend to be used more in these applications. These are color-coded green, by the way, for the APC. The UPC, SPC, and PC are color-coded blue, and the multimode can be black or beige. And in the cases of laser-optimized fibers, maybe the aqua color code. So what are the different types of connectors? Here we show some variations of some of the more popular ones. Up at the top is an SC UPC on single mode. The second one, SC APC on single mode fiber. An LC single mode fiber, UPC polished. And down at the bottom is a single mode ST type. But each of these have different ferrules that require adapters and test jumpers. And people may say, well, the 2.5 millimeter ferrule in an SC is the same as in the ST. Well, the diameter is the same, but not the length. And they vary connector to connector, and different manufacturers specialize in just ferrules and adapters. And then the cleaning products used to clean the in face and the inside of the adapters and the surface of a mating connector may differ on each of these based on mechanical geometry and the cleaning technique used. Okay, start off with a few of these. First, the subscriber connector, and that's what SC technically stands for, and that it was meant as a push-pull connector from the very early days when it was released. It uses the push-pull mechanism. It's specified by the IEC 61754 standard. It's the -4 nomenclature, and the fiber optic connector interrepeatability interconnection standard. 2.5 millimeter ferrules, simplex duplex, multi-mode single mode, keyed, push-pull design, and color-coded. Another the variation of the SC connector is the hardened SC. This is a term specified by the Telcordia General Recommendation 3120, which allows for installing into the field a hardened version of the SC connector, UPC or APC polish techniques, environmentally sealed, and these are very common in fiber-to-the-home installations because of the cost of doing single fiber terminations in the field is so high, so it's better to have a factory-built drop cables manufactured as well. Other examples of this type connector, though, are the MPO and MTP, which are also being manufactured in hardened drop cables as well. Another common connector is that developed and invented by Norm Lampert while at AT&T, and it's the LC connector. The LC connector is not an acronym. A lot of people think it is. It's not. Norm Lampert himself said, he goes, no, it was done at AT&T. It's not Lucent connector because it was done prior to Lucent, number one. Number two, it's not named after Norm, and that even though he's flattered by it. It's just literally LC because it sounded good. But it was the first small form factor connector which gave double the density of the terminations versus the SC type connectors. And to reduce the size, a couple things happened. We had to reduce the ferrule diameter to 1.25 millimeters. We also had to reduce the strain relief side in the rear. So an LC connector has approximately 70% of the tensile strength of an SC for pull tensile strength. And again, it's a push-pull connector and available in both multi-mode and single-mode variations. The difference here on single-mode and multi-mode is that multi-mode tolerances are looser than single-mode, and therefore single-mode fiber tolerances are tighter, the single-mode ferrule tolerances are tighter, the single-mode sleeve tolerances are tighter, and so you just can't always say, well, use a multi-mode sleeve on a single-mode system, because if you do, you're getting looser tolerances, which means worse performance. You can always use a single-mode sleeve, though, on a multi-mode span to get better performance. Now, the bayonet fiber optic connector 2.5 /2.5 millimeters is commonly known as the ST, and there's two variations, both of which are shown. The ST, the standard's at the bottom. You can see the cutaway indent for the bayonets on the coupling mechanism. And up at the top, you'll see that there is no straight cutaway. It's inside, which means the adapter's a larger diameter. It also is longer. And for anybody that's ever had problems where an ST2 does not mate properly, it's because you're using an active device receptacle on a piece of equipment, and that longer and wider housing will not allow it to mate fully because of the jam nut used on the equipment. So you have to use an standard ST connector in that circumstance, but that's the reason for it. And this was the de facto standard for terminations in the 1980s and 90s, especially with the multi-mode environment. The single mode was using the FC connector and that as well, which isn't shown here, but it was fiber connector and it was a threaded type using a 2.5 millimeter fiber. Another type of connector that's evolving is the multi-fiber connectors, in particular the MPO-MTP version. So this can deal with ribbons, single mode up to 24 fibers, multi-mode up to 72, and a single coupling. And on a lot of the fiber to the home or fiber to the building installations, we're seeing versions with terminations at patch panels, where you connect patch panels on different floors with cables that have MPO connectors on each end, and they're easily spooled out and slack taken care of and addressed. One thing with a ribbon connector, there is an angle on the interface, so the polishing, the cleaning is unique to these connectors. You have to get the right cleaning materials. You have to have the right adapters for cleaning. And you also have to have the same for the adapter sleeves as well for alignment. There's also, if you notice, the plugs on the bottom, is they have pins. These are alignment pins. So the cleaning materials have to be able to clean the fibers which are in between those pins. So it's a special cleaning product that you would have to order specific to this. Very good connections. They have very high density, becoming very popular. They're definitely a mature product today. So now that we know the connectors, there's still the issue of the different type of termination options, and there's different techniques. For example, on single mode, it's not recommended to field terminate with a thermal cure anaerobic. And it's not the bonding technique that's the problem. The problem is the polishing technique, and to maintain a spherical polish over the ferrule and the fiber end, and holding the minimum attenuation of the connection itself. Now, so what is the single mode industry or the service providers have done over the years, they've ordered pre-terminated pigtails, which is half of a jumper, but normally with either a 250 micron or a preferred 900 micron coating. And these are spliced onto the cable via splice tray. And the other end is cleaned and then inserted into the patch panel to the correct location. But now we have some choices in that. Over the years, manufacturers have made different types of splice-on connectors, and these can be directly terminated onto a single-mode fiber. And to explain how they work is there's basically a mechanical splice inside the plug assembly itself using index matching fluid. So the index matching fluid reduces the Fresnel reflections inside the connector, the plug assembly, and the in face, the APC or UPC, is factory polished, so we're in control there. So the difference here is you really require a very good cleaving tool. It's the number one issue. If you're going to do field terminations on single mode, you would definitely want a quality cleaving tool. And there's also techniques of these that have now made where you can terminate using a fuse connect process where the plug assembly is put into a fusion splicer and fused to the pre-terminated fiber stub that's a pre-polished fiber stub in the plug. So again, the critical component is the cleaving tool. They have low loss, they give you high yield, and I hope everybody writes down that word yield because we're going to talk about it, how important it is, and what it's saying is how many are good the first time. And so whether it's a splice-on connector, the unicam type, the no polish type, we're still looking for low attenuation reflectance to meet the ITU or Telcordia or TIA standards, and giving us quality in phases. Here's an example of the difference between a single mode termination and multi-mode. One thing, single mode terminations have a much smaller core versus the 50 or 62.5 micron core of the multi-mode. Much tighter tolerances on single mode fibers versus multi-mode. The polishes are critical for single mode because the 1310 and 1550 nanometer wavelengths require either the use of the Fabre Pro or the DFB lasers, where on multi-mode, the LEDs are not even affected by reflectance, and VCSEL light sources are reflection insensitive. And so you can get away with much higher reflection values at 850 nanometers than you can at 1310 or 1550 nanometers. So correspondingly, the test equipment and measurement equipment is more complex as well for both of these. Now, the ferrule inventory, pretty much today, we pretty much have standardized, but in the older days, you had to have a different ferrule for different size fibers because the tolerances were worse. As the tolerances have improved, for example, a single mode fiber today is 125 plus or minus 0.7 microns. Years ago, it was 125 plus or minus 2, So you had to have an inventory. Multi-mode, where the tolerances are 125 plus or minus 2 today, you can pretty much have a much larger 128 micron inside diameter ferrule, and it'll work on all of them. And the core size is so large that you can still meet the 0.75 dB TIA 568 standard relatively easily. But the reflection issue, again, it comes back to the lasers that are used in single mode system versus the light sources used in multi-mode systems. Now, installed cost, one of the reasons that the service provider industry worked with factory terminated pigtails was that the in-face was already polished to meet the reflection values, and we needed to simplify the tooling for technicians in the field. And so the use of fusion and mechanical splices has been the dominant termination technique for decades, whereas in the multi-mode side, there's a lot of connections at a smaller density installations, and so you'd have a field technician and doing his figure 8 polishing and bonding as many connectors as he could in one location. And that was easy to do because the fiber tolerances weren't as great and the core size was so large in that. And so the installed cost on the service provider side was a very high yield on single mode because of the equipment that they were investing in, and that was the tooling, whether it's a fusion splice or a cleaving tool, versus in a field technician where the tooling was very simple. Okay. Multi-mode termination techniques, on the other case, has historically been the thermal cure epoxy or anaerobic epoxy, UV epoxy or adhesive in the past. While no polish and fused connections are around for multi-mode, there's a big cost difference in these plugs. A $2 thermal cure anaerobic plug is a pretty minimal cost versus paying $10 to $20 for one of the splice-on connector types. So as a contractor or a user, you're looking at that cost, and there's a day and night difference. And this is why yield is so important. That's how many are good the first time, so that we minimize the loaded cost of an installation. But for any manufacturers that are here, a lot of these same values still apply, is saying you have to invest in your tooling, you have to maintain costs, you have to meet a performance requirement, and you should be monitoring your yield on how many are good, because if you're having a yield problem, you're wasting money, you're wasting time. And again, the last 6 slides are going to talk about yield. move on to what the interface looks like. So here's some examples of some problems that can potentially exist. And on the 62.5125 in epoxy filled cavity, that's because it's a thermal cure epoxy that's used for the termination technique. And the epoxy, if it's not removed, and that it's going to create a gap, or it's going to force a gap between the plug interfaces, which is going to increase reflectance and attenuation. Broken fibers are pretty easy to resolve. You can see the effect of skin oil and the use of isopropyl alcohol on a fiber interface. One thing about isopropyl alcohol, it's not recommended for laser-based systems because it can increase the reflectance of a connector, and it's because of this residue that's left on the fiber interface. Now, this is an example of the IEC 61300-3-35 standard. I know these things just roll after a while. But this is a single mode example. The multi-mode example is actually a larger area. For example, zone A is from 0 to 65 microns for multi-mode, and zone B is 65 to 120 microns. But if you're involved with connectorization, I suggest that you buy these standards, and that so that this way you can see what you should be testing and inspecting too. Excuse me. So one other thing to pay attention to is the cleaning instructions. Manufacturers spend a lot of time recommending cleaning products for their products, and these aren't necessarily the connectors. If you're a manufacturer of a high-end piece of test equipment, you are putting recommendations to the purchasers of your equipment, the users, to say, use this product. And the reason that they're recommending these products is they've already measured and evaluated the effects of different types of cleaning materials. So you do need to pay attention to the system manufacturer's perspective on cleaning. You also need to recognize that in the past, cleaning was performed to prevent physical damage. Today, it's critical to reduce reflections for systems using laser sources, and especially DWDM systems, which is the worst case of all. You have to identify on contamination what the contaminant is to identify the right cleaning solution to be able to resolve the problem. You also need to find out the right product to use, whether it's going to, for the application, are we cleaning the surface of a ferrule, cleaning around the ferrule, are we cleaning inside a sleeve? Okay. So now let's get to these 6 slides I've mentioned. So it's about yield. Now, from a manufacturer perspective, you want to look at this as one to say, I want to build as many assemblies as I can with the highest performance and the least amount of waste possible. From an installer perspective, you want to decrease your labor cost as much as possible by having good quality workmanship. And by doing so, it may cost you more to buy a better quality product at a higher price, but your yield goes up. So what you should be working on is looking at the value of the installed cost or the loaded cost of a termination. And so yield's defined as the number of connectors that test good. So we're going to show an example using a 90% yield in a minute. The cost of the connector is minimal compared to the installation labor, especially in the field. And each repair cycle involves additional retermination testing, which is a different labor cycle being added. And then following procedures is critical, and the best desirable effect is the least amount of failures. Okay? And there are some terminations can be salvaged. But let's look at this example. In this case, let's just say we're installing a 48 fiber cable between 2 buildings. The contractor's responsible for the installation of the cable and the termination of the 48 fibers, which means that we have 96 total terminations to do. They're also responsible for the final testing and documentation of the system. So in this case, we're going to make an assumption of a 4 dB allowable not to exceed loss budget, and I'll explain this later as we move. But out of the 96 terminations, 10 are bad. Now, I'm just going to round this 96 up to 100 for easy math. So 10 are bad, so it's a 90% yield. So the job now changes to locate and re-terminate the bad connectors. Actually, it's plugs. And then you have to retest. However, every time you retest, remember you got two buildings. That means you have one person at one end and you have another person at the other end, which means that you have another labor cycle. Okay, so let's go to the next slide here, and if we look at this, you say that out of those 10 reterminations with a 90% yield, 9 of the 10 that need to be done should pass again. That's 90% yield, which means that we're now going to go to a third cycle. But after you re-terminated those 10, you have to retest to confirm the attenuation and that you did get the values that you want. So again, we added a cycle. Okay, so the third cycle is to re-terminate that last connector, that last plug, and you have to retest it again. So we ended up in this perfect world of a 90% yield of 107 total terminations versus the 96 we started with, which means for anybody planning terminations, you better add in some spares based on your yield count. And if you don't monitor your yield values, that means you're going to end up sometimes having to pull off a job because you had to order 1 or 2 more plugs, and that you always want to have extra versus short. And you ended up going through 3 labor cycles of 2 technicians each to perform all this work. So you had not only a waste of parts, but you had labor cycles involved. Now, keyword here is where we said in a perfect world. Okay? What really occurs? Okay, during the second cycle, the technicians did not use the proper test equipment to exactly identify which connectors were bad. Instead, they thought mechanically rather than optically and cut off several good terminations. And the last slide, we're going to talk about this effect. But for now, use inspection scopes to identify surface damage and contaminants. Use visual lasers on short spans to identify internal breaks in the connectors. And you can identify breaks inside the ferrules, which would be a surface damage, or during the insertion of the fiber where the fiber broke because of improper technique and that. But you can also create a macro or micro bin at the end of the connector on the cordage to check for continuity. This doesn't mean bending it at 180 degrees. It just means bending it enough to get continuity of red light from where the technician is. Then the higher end piece of test equipment, use OTDRs to recognize a good launch. So if it's a poor launch, in other words, the trace and that you're getting on your OTDR screen, if it's a poor launch, that means the problem's on the front end of the span. And that. At the same time, if you're getting a good launch, but you're getting a far end, a poor Fresnel reflection at the far end, that tells me it's the far end termination that's bad. So before I cut off any plug, I want to make sure that I know that it's the right plug to turn off. Okay, so here's an example where we take 6 fibers and that. So the blue fiber, the first fiber, we see our light source is emitting light at minus 10 dBm, our OPM's at minus 13.7 dBm. If I zeroed the meter, it would just show with a loss of 3.7 dB, and that's a very good value. And that the second span, the second fiber, shows that we have a loss of 18.7 dB, so obviously we have a problem there. The third fiber is the loss of 5.4 dB, so we have another problem there. The brown and slate fibers have been rolled, and so we're not getting a measurement on either of those. And then the white fiber, number 6, is a loss of 4.1 dB. So let's review these. Well, first thing, the simplest thing, anytime that you get 2 fibers that are dark, one after another, there's a good chance they've been rolled. So what you do is you move your power meter over to the next fiber and check for power, and if that's the case, then it's a real quick process of finding out which end is rolled in properly. Roll them back and get your measurements for your final. Okay. The white fiber, the last fiber, the losses 4.1 dB are not to exceed values 4.0. I would look at this as a cleaning issue first, and that rather than a re-termination. Remember, the connector repeatability standard is 0.2 dB. So we do want to make sure that we do fall into the right values. So don't re-terminate if you don't have to. And most time when you're in a couple tenths of a dB, cleaning will take care of it as well. And that may mean that you have to clean your test jumpers. Actually, you should always clean your test jumpers and inspect them prior to any test being done. So this brings us back to the orange and the green. And if you notice on the upper left of the orange where it starts, there's an angled dash line there. What that means is that fiber's damaged at the front end. and that where on the green fiber, the loss is damaged on the far end. Now, the way that it will come out measuring, though, with the power meter is the front end damage will show a higher loss at the receiver, where the far end damage will show as a lower loss at the receiver. And this is primarily caused by the fact that the photodiode in the power meter is about the size of a pencil eraser, and it's relatively large size, so any light, say, coming off the green fiber will diffuse, but the photodiode can still pick it up, even over a short test jumper. And so we're receiving a measurement in that. At the same time, the diffusion of the light from the orange fibers earlier, some distance away, and so the attenuation of the fiber and over distance is diffused to the point where we get a real high loss. Now, if you're thinking mechanically, what the technician's going to do is this is the higher loss. They're going to cut off the orange fiber at the right end, on the right side, not the left side, and on the green, they're going to do the opposite effect. They're going to measure it from the other end. They're going to see the higher loss go in the opposite direction. So both the orange and the green were re-terminated incorrectly. They terminated the wrong end and that. And this is where it's critical to use your test equipment to find the right end first. Okay, so I hope that we filled in a lot of details on fibers and connectors and the importance of this. So we have a whole variety of questions here. So let's go into some of these. Okay, there's one. Have you heard about a non-contact fiber optic connector with a 0.1 dB insertion loss, 7 dB return loss, and lasts 10,000 matings? No, but I would love to know who it is. But I can give you a couple examples where I think it may be, but I would have to know more specifics. One thing on when you get very low attenuation of 0.1 dB, the point could be that that's made in a factory-controlled environment, and it's measured in a factory-controlled environment, not in a field environment. In other words, you take a piece of fiber, cut it in the middle, put it back together, same core, same cladding, same tolerances all the way around. The insertion loss, it could be anti-reflective coatings. It could be a lensed connector very easily. And because it's a lensed expanded beam connector, it could last for 10,000 matings because you're not doing surface matings. There are some other materials, tungsten carbide ferrules, for example, that don't wear like ceramic ferrules do. So anyway, I would have to know more about the specific vendor, but I always look at these, and next week is the Optical Fiber Conference in Anaheim, California, and this is a good opportunity for all of us in the fiber industry to check and see and talk to the vendors and manufacturers and their results. There was a question, didn't think there was index matching gel in a fuse-on connector. No, there's not in a fuse-on. It's on the splice-on connectors. The no-polish types are as well. Okay. The LC connector, have you seen some installations where release tap was moved under locking tab? I'm not sure that I'm hearing that. Told that you can lock secure connectors. True, could be. There's a lot of variations of a lot of these different connectors, and because of security applications, it wouldn't surprise me if there's a feature that's out there. Let's see. Okay, that's about it. Apparently we're having a time problem here and such. So I hope that the information you found is valuable. In case you want further information, you can also reach me, Larry, at lightbrigade.com. There's also information on, we have a whole series of DVDs that go into more detail. Actually, the connector DVD has 12 chapters. I just picked pieces of each of those to present here to talk about a lot of topics that come into just terminations. And in a future session, I'd like to go into more detail on each of these different components. I'd love to hear from you on what topics you would like to see as well, and that for you. And that. So let me hand off over to Jim for a minute. Oh, okay. I'm supposed to read these off. Sorry. To see more information, of course, on our collection of training DVDs, you can actually, on YouTube, you can go to Light Brigade DVDs and get the introductory chapter on any of these, and that's no cost. And then full description on our website about our different courses, and of course half of our courses we do are custom courses internationally. And you can also contact us at the email address shown, or you can reach me personally, Larry@lightbrigade.com, and both our international and domestic numbers are shown on the screen.
Great. Thanks, Larry. On behalf of Lightwave and Penwell Corporation, I want to thank today's speaker, Larry Johnson, who is the founder of the Light Brigade, and the Light Brigade themselves, who sponsored this. Today's presentation, Fiber Optic Connectors, as we told you earlier, is available for download probably starting tomorrow evening at lightwaveonline.com, where you can get this entire presentation and view it again. We want to thank you today for joining us and look forward to our future webcasts. We're going to start holding them the last week of every month, and you'll get notifications about that. Greatly appreciate your time. Thanks for attending.